In this episode, we're going to take two problems that often feel chaotic to beginners and make them feel structured and solvable. Failures when one system cannot talk to an API, and failures when an agent cannot talk to the control plane that manages it. An application programming interface, API, is the boundary where software asks another service for data or action, and an agent is a small helper program that runs on a device and reports status or performs work on behalf of a central system. When either of these communication paths breaks, the symptoms can look the same at first, like timeouts, missing updates, or jobs that never complete. The good news is that communication failures usually fall into a small number of categories, and if you learn to sort evidence into those categories, you can move from confusion to a clear explanation. The skill is not typing commands or changing settings, but thinking like an operator. You separate reachability from trust, trust from permission, and permission from correctness. Once you can do that, you can tell whether you have a network path problem, an identity problem, a policy problem, or a service health problem. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. The first mental shift is to stop treating communication as one thing and start treating it as a chain with links that can fail independently. A client must know where to send a request. It must be able to resolve that name or address. It must be able to reach the destination over the network. It must establish a secure session if encryption is required. It must present identity, and then it must be permitted to do what it is asking. After that, the server must be healthy enough to process the request and return a response in time. Agent communication has the same chain, plus a few extra links because the agent often runs behind firewalls, uses periodic check-ins, and may depend on local system health like time synchronization. When you hear a phrase like the agent is offline, that is not a diagnosis. It is a symptom that could be caused by any broken link in the chain. Operators troubleshoot by finding which link is failing, not by guessing at the final root cause. This keeps the process calm and repeatable, and it prevents you from changing things randomly that might make the situation worse. Start with reachability, because if you cannot reach the destination, nothing else matters yet. Reachability failures often show up as timeouts, connection refused messages, or errors that suggest the request never got a response at all. In an API scenario, this can mean the service is down, the address is wrong, name resolution is failing, or a firewall is blocking traffic. In an agent scenario, reachability can fail because the agent cannot reach out through a network boundary, because outbound access is restricted, or because a proxy is required and not configured correctly. Beginners sometimes assume a timeout means the server is overloaded, but timeouts are also common when the client is trying to reach something that does not exist on that path. Operator thinking asks, can we prove the destination is reachable from the place that is failing, not from our own laptop or a different network? Evidence matters because a service can be reachable from one segment of the network and unreachable from another due to segmentation or policy. When you anchor on where the failure occurs, you stop arguing and start isolating. Once reachability is established, the next link is secure session establishment, which is often where subtle failures hide. Transport layer security, TLS, is used to encrypt traffic and verify the server's identity through certificates, and it can fail even when the network path is open. A certificate might be expired, misconfigured, signed by an untrusted authority, or mismatched to the server name the client is using. In a beginner's mind, this can feel like random breakage because the service is clearly online, but the client refuses to proceed. The operator mindset is to treat this as a trust failure, not a network failure, because the client is intentionally not completing the handshake. Agent communication is especially sensitive here because agents often pin trust to a particular certificate chain or are less forgiving about unusual configurations. Another twist is that some environments intercept encrypted traffic using corporate proxies, which can cause trust errors if the agent does not trust the proxy certificate authority. When you recognize that reachability and trust are different, you stop chasing the wrong fixes and you start asking the right questions about certificates and identity. After trust comes authentication, which is the system proving who it is, and then authorization, which is whether it is allowed to do the thing it is asking. These failures show up as responses that clearly deny access, like not authenticated or forbidden. For APIs, this often involves tokens, keys, or other credentials that can expire or be revoked. For agents, authentication might involve a registration process, a client certificate, or a shared secret that ties the agent to its controller. Beginners often confuse authentication failures with network failures because the service is responding, but the desired work is not happening. Operators interpret denial responses as good news in a strange way because it proves the service is reachable and awake enough to enforce policy. That means you can focus on identity, credential freshness, and permission scope rather than wondering if the service is down. It also means you should avoid repeated retries with bad credentials, because that can trigger lockouts or security alarms. Clear thinking here helps you both fix faster and avoid creating a bigger incident. Now consider request correctness, which is where an API communication failure can be entirely self-inflicted by the client. A request can be sent to the wrong path, with the wrong method, missing required headers, or with a body that is malformed or fails validation. These issues tend to produce predictable client-side error responses rather than silence. In an operations context, these errors often appear after an update to automation code, a configuration change, or an environment change, such as a new base URL or a new version of an API. For agents, request correctness can be about the agent sending malformed payloads due to a bug or local data corruption, or it can be about the controller rejecting older agent versions that do not match the expected protocol. The operator habit is to compare a failing request to a known good request and look for differences, because differences are where causes hide. Even as a beginner, you can understand this conceptually. If one client succeeds and another fails, the request is probably different. That guides you toward inspecting what is being sent, not just the error you received. Service health and dependency health are the next link, and this is where server-side failures and inconsistent behavior show up. A service can be reachable, can establish secure sessions, and can authenticate clients, but still fail because it is overloaded, misconfigured, or dependent on something that is down. This can produce errors in the server-side category, or it can produce slow responses that look like timeouts to impatient clients. For agent communication, a common pattern is that the controller is partially functional. It accepts check-ins but cannot schedule jobs, or it schedules jobs but cannot record results. Another pattern is that the agent reports in but jobs fail because the agent cannot reach a package source or internal dependency, which makes it look like an agent issue when it is actually an environment issue. Operators look for consistency, such as whether failures affect all clients or only a subset, and whether failures correlate with load spikes or maintenance windows. They also look for secondary symptoms, such as increased error rates on related services, because dependencies often fail together. The goal is not to guess which dependency is down, but to confirm whether the problem is systemic rather than isolated to one client. Time is an underrated link in this chain, and it matters more for agents than most beginners expect. Many authentication systems rely on timestamps, token expiration, and clock skew limits, meaning a device with the wrong time can appear to have invalid credentials even if the credential itself is correct. Agents also rely on schedules for check-ins, and if timekeeping is broken, they can appear offline or can check in at odd intervals. From an operator perspective, time issues are dangerous because they create inconsistent symptoms. The same request might succeed on one machine and fail on another purely because of clock differences. Time issues also interact with certificates, because certificate validity windows are time-based, and a device with a clock in the past might treat a valid certificate as not yet valid. You do not need to know how to fix time synchronization to understand why it matters, but you do need to remember it as a category when communication fails in puzzling ways. When an issue looks like random authentication trouble across a small subset of devices, time becomes a prime suspect. That kind of pattern recognition is part of becoming effective at troubleshooting. Another frequent cause of agent communication breakdowns is local constraints on the device that prevent the agent from operating normally. The agent might be running but unable to write logs, unable to allocate enough memory, or blocked by local security policies that restrict network access. It might be stopped, corrupted, or repeatedly crashing, which makes it appear as if the controller cannot reach it, when in reality the agent is not stable enough to maintain contact. Operators separate controller-side evidence from device-side evidence by checking whether the controller is receiving any heartbeats, whether the device shows partial signs of life, and whether the problem is clustered around certain device types or configurations. If every device in one environment goes offline at the same time, that points to network or controller issues, not local device issues. If one device goes offline after a local change, that points to a device-side cause. This is not about blaming the device. It is about narrowing the scope so you know where to look next. The earlier you can define scope, the faster you can resolve. Proxies, gateways, and middle boxes deserve their own attention because they can cause failures that look like the API or agent is broken. A proxy can block certain destinations, require authentication, rewrite headers, or inspect traffic in ways that break secure sessions. A gateway can time out idle connections, enforce rate limits, or apply rules that differ depending on the source. In agent communication, this is especially common because agents often run from networks with strict outbound controls, and the difference between allowed and blocked can be a single rule change. Operators therefore ask simple but powerful questions like, did anything change in the path, and do other clients on the same path show the same problem? They also consider whether the failure is consistent with policy enforcement, such as a sudden spike in forbidden responses. Even without deep network knowledge, you can carry the operator habit of remembering that the path matters, not just the endpoints. When you treat the network as an active participant, you avoid false conclusions about the service itself. A disciplined way to troubleshoot, without turning it into a checklist recital, is to frame your observations as yes or no answers to the chain links. Can the client resolve the destination? Yes or no? Can it reach the destination? Yes or no? Can it establish trust? Yes or no? Can it authenticate? Yes or no? Is it authorized? Yes or no? Does the request match the contract? Yes or no? Is the service healthy enough to respond in time? Yes or no? For agents, you add, is the agent running, and is it checking in at expected intervals? Each yes answer moves you forward, and each no answer tells you where to focus. This approach prevents the common beginner problem of trying 5 fixes at once, then not knowing which one helped or hurt. It also produces a clean explanation you can share. The network path is open, but trust fails due to certificate validation, or the agent can authenticate, but is forbidden from scheduling jobs due to permissions. Clear explanations are valuable because they lead to targeted remediation rather than broad disruption. The last piece is learning to recognize patterns that distinguish API communication failures from agent communication breakdowns, because they often overlap but have different rhythms. API failures are often immediate and request-driven. You send a request, you get an error, or you do not. Agent breakdowns often involve timing and state. The agent checks in periodically, and the failure shows up as a missing heartbeat, stale status, or backlog of tasks. API failures often affect a specific endpoint or a specific method, while agent failures can affect whole groups of devices depending on network location or policy. When you see delayed symptoms, like jobs piling up or status slowly going stale, think agent or controller behavior. When you see instant rejection codes or immediate timeouts for a single call, think API path, request format, or authentication. Operators do not rely on one clue, but they do use these differences to choose the next best evidence to gather. That is how you stop feeling stuck and start moving toward the root cause. To wrap this up, remember that communication failures are rarely mysterious when you break them into the same few categories and let evidence guide the next step. Network reachability problems stop the conversation before it begins. Trust problems stop it at the handshake. Authentication and authorization problems stop it at the boundary of identity and permission. Request correctness problems stop it at the rules of the API, and service health problems stop it at execution time. Agent communication adds scheduling, device health, and local constraints, which introduce time-based and scope-based patterns that can look confusing at first. When you train yourself to identify which link is broken, you stop treating failures as personal puzzles and start treating them as solvable system behaviors. That is what operators do, and it is also what this certification expects. Not that you memorize every error, but that you can reason your way through the failure with calm, structured logic. If you keep that chain model in your head, you will find that many failures become predictable, and predictable failures are the ones you can fix safely without making the blast radius larger. 123,456. Go. Episode 65. Troubleshoot application failures and certificate issues in automated deployments. In this episode, we're going to connect two types of failures that often show up together during automated deployments: the application that will not start or will not behave correctly, and the certificates that make secure communication possible. Continuous integration, CI, and continuous delivery, CD, pipelines can move changes quickly, but they can also move problems quickly when the environment is slightly different than expected. When a deployment fails, beginners often focus on the last error message they saw, but operators focus on the first meaningful symptom and the conditions that made it appear. Certificates add an extra layer because the application might be healthy, but it cannot prove identity, cannot establish trust, or cannot negotiate encryption. The goal is to learn how to reason about these failures without panic, without random changes, and without blaming the pipeline as if it were a mysterious force. By the end, you should be able to describe what kind of failure you have, what evidence supports that conclusion, and what a safe next step would look like. A good place to start is to separate deployment success from application success, because they are not the same thing. A pipeline can report that it successfully delivered files and started a service, while the application fails moments later due to configuration, missing dependencies, or startup checks. This mismatch is common because automation measures what it does, not always what the application becomes after it runs. Operators therefore treat a deployment as complete only when the application is healthy according to its own health signals, not just when a task finished. That mindset makes certificate issues easier to diagnose because many certificate failures appear only when the application makes its first outbound call or accepts its first inbound secure connection. If you only look at the deployment step, you might miss that the real failure occurs during runtime communication. So the first operator move is to anchor on the timeline. What changed, when the failure first appeared, and whether the system ever reached a stable running state. Application failures in automated deployments often cluster into a few predictable buckets, and naming the bucket is half the battle. There are startup failures, where the process cannot launch or immediately exits. There are runtime failures, where the process launches but crashes or behaves incorrectly under load or when it touches a particular dependency. There are readiness failures, where the application is running but not ready to serve traffic, which is common when it needs to warm caches, apply migrations, or connect to external services. And there are functional failures, where everything looks healthy but the application returns incorrect results due to a misconfiguration or a mismatch between versions. Certificates can influence each bucket, but they most often appear as readiness or runtime failures because secure connections are frequently a prerequisite for the application to consider itself ready. When you know which bucket you are in, you can stop chasing irrelevant causes and focus on the classes of evidence that matter. Another common certificate problem is name mismatch, which is easier to understand if you think like a cautious client. A certificate typically asserts that it is valid for a specific name, and the client compares that name to the destination it believes it is reaching. If the client connects using a different name, like a short host name instead of a fully qualified domain name, the client may refuse the connection even if the certificate is otherwise correct. Automated deployments can trigger this when environments differ, such as staging using one naming scheme and production using another. It can also happen when traffic is routed through a load balancer or gateway that presents a certificate for one name while the client expects another. Operators spot this by focusing on what name the application is using at runtime, not what humans call the service in conversation. The mistake beginners make is to assume the certificate is wrong when the targeting is wrong, or to assume targeting is right when the certificate was issued for a different identity. Keeping identity and addressing separate helps you troubleshoot with less frustration. Certificate chain issues also show up frequently, especially when services rely on intermediate certificate authorities. Certificate authority, CA, chains are often built from a leaf certificate, one or more intermediates, and a trusted root. If the chain is incomplete, clients may fail to validate even though the leaf certificate looks fine. This can be environment dependent because some clients already have certain intermediates cached or installed, while others do not. In automated deployments, chain issues can appear when new instances start clean and do not have the same trust store history as long-running systems. The result is inconsistent failures that look like flakiness, but the underlying cause is deterministic. The client cannot build trust. Operators therefore pay attention to whether failures correlate with new instances, container restarts, or fresh nodes. If only new deployments fail while old ones still work, a chain or trust store change is a strong possibility. This is a powerful pattern to recognize because it turns a confusing symptom into a clear hypothesis. While certificates are a major theme, many automated deployment failures are not cryptographic at all, and operators keep those possibilities on the table. Applications can fail because configuration values differ between environments, because required dependencies are not available, or because the application is expecting a resource that is not present. A classic example is an application that runs locally but fails in deployment because it depends on an external service that is blocked by network policy. Another is an application that expects an environment variable or secret, but the value is missing or malformed, causing startup checks to fail. These problems can masquerade as certificate issues if the first external call is a secure call, because the error surfaces at the connection boundary. The operator move is to correlate the error with what the application was attempting to do at that moment. If the failure happens before any outbound call is attempted, it is likely a pure application startup issue. If it happens exactly when connecting to a secure endpoint, certificates become a primary suspect. Readiness and health checks are another area where certificate issues and application issues collide. Many deployment systems use health checks to decide whether to route traffic, mark a release successful, or roll back. If the health check endpoint itself requires secure access and certificates are misconfigured, the system may mark the application unhealthy even if it would otherwise run. Conversely, if the health check is too shallow, it can return success while deeper dependencies fail, causing the deployment to pass, but users to see errors. Operators think about what the health check truly proves, and they treat it as a measurement tool with limitations. A certificate failure during health checks often signals a mismatch between how the application is configured for secure connections and how the environment expects those checks to be performed. The key is that health checks should align with real user paths without being so fragile that minor certificate renewal timing creates false alarms. Balancing that is a design task, but troubleshooting starts by understanding that health checks can be the messenger, not the villain. Version mismatches can also cause application failures that look like certificate problems, especially when secure protocols change. An application might be updated to require a newer protocol version, a different cipher suite, or stricter certificate validation behavior. In that case, older dependencies or older peers might not negotiate successfully, and the failure appears at connection time. Beginners might interpret this as random security breakage, but operators recognize it as compatibility drift between components. Automated deployments can make this worse if different parts of the system roll out at different times, producing a window where new clients talk to old servers or vice versa. This is where careful observation of which direction the failing connection goes becomes important. If only the newly deployed version fails to connect, it suggests the new version has stricter requirements or different expectations. If only the old version fails after a change, it suggests the environment now enforces stronger security and older components cannot comply. Either way, the problem is compatibility, not mystery. Secrets and certificates are closely related in troubleshooting because they are often managed, rotated, and distributed by automation. A certificate might be treated as a file, a secret, or a managed object, and failures can occur when the wrong version is delivered, when renewal timing is off, or when permissions prevent the application from reading it at runtime. Even without touching implementation details, you can understand the operational risk. If automation rotates certificates, but an application does not reload them correctly, you can get failures that appear hours later when the old certificate expires. That delayed failure pattern is a classic clue that rotation and reload behavior are misaligned. Operators therefore ask when the certificate was issued, when it expires, and whether failures correlate with those times. They also ask whether the certificate used by the application is the one the team thinks it is using, because stale copies can persist across deployments. The lesson is that certificate issues are often lifecycle issues, not just correctness issues. When you troubleshoot under pressure, you want a calm way to gather evidence without changing the system blindly. Operators start by identifying whether the failure is consistent or intermittent, because intermittent failures often point to load balancing, partial rollouts, or inconsistent configuration across instances. They then identify scope. Does it affect one service, one environment, one region, or one set of newly deployed instances? They compare a known good request path to a failing path, even if that comparison is conceptual, such as old version versus new version or instance A versus instance B. They interpret error categories, separating network reachability, TLS trust, authentication, authorization, and application logic. This process does not require any particular tool, but it does require discipline in how you form hypotheses. The reason this works is that communication and startup failures obey patterns, and patterns become visible when you keep the scope and timeline clear. The moment you lose track of scope, you start guessing, and guessing is how outages get extended. A common misconception is that certificate issues always mean the certificate is wrong, when many times the certificate is fine and the environment context is wrong. The application might be pointing to the wrong endpoint, might be using an unexpected name, or might be running with a trust store that lacks the necessary certificate authorities. Another misconception is that turning off validation is an acceptable quick fix, but that trades a reliability issue for a security failure, and it often creates a bigger incident later. Operators treat trust validation as a safety feature, not an annoyance, because it prevents man-in-the-middle conditions and misrouting errors from becoming silent. Another misconception is that application failures are always caused by code changes, when configuration and environment differences are equally common. Automated deployments increase the rate of change, which increases the need for careful reasoning about which change actually triggered the failure. If you keep these misconceptions in mind, you will be less likely to chase false certainty and more likely to find the real cause. To close, troubleshooting application failures and certificate issues in automated deployments is mainly about separating what is failing from what is merely present in the environment. Certificates are part of a trust system, so their failures often show up as secure connection problems even when the service is reachable. Application failures can be startup, readiness, runtime, or functional, and secure communication can be a trigger point that exposes those failures. Operator thinking uses a chain model, moving from reachability to trust, then to identity, then to permission, and finally to application behavior and dependencies. Along the way, you look for patterns in scope, timing, and version differences, because patterns convert confusion into a small set of plausible causes. You do not need to memorize every possible error to be effective, but you do need a stable method for interpreting what the system is telling you. When you can explain the failure category clearly and justify it with observations, you are no longer stuck, and you are far more likely to fix the problem without expanding the blast radius.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.